Hello students, welcome back to my channel Samina's Telugu Pharmacology. In this video of fluoroquinolones part 2, we are going to see about the classification, mechanism of action and resistance of fluoroquinolones. So the fluoroquinolones was discovered in the 1980s and this was a breakthrough in the achievement of antibiotics. So if you see, the fluoroquinolones were discovered by fluorination of quinolone structure at position 6 with a fluorine moiety, as well as the substitution of 7th position with a piperazine ring. So here you can see this is the quinolone structure and this is the fluoroquinolone structure, and the drug is ciprofloxacin. Here at position 6 fluorine moiety was added and at position 7 is substituted with piperazine ring. What are the advantages that fluoroquinolones show over quinolones is that fluoroquinolones are highly potent in nature. They show expanded spectrum of action. That is, where fluoroquinolones show their mechanism of action only on gram-negative bacteria, while fluoroquinolones show their mechanism of action on gram-positive bacteria too. There will be a very slow development of resistance in case of fluoroquinolones because fluoroquinolones exhibit a unique mechanism of action. Fluoroquinolones show better tissue penetration and good tolerability. Coming to the classification of fluoroquinolones, there are two major classes of fluoroquinolones, that is the first generation fluoroquinolones and the second generation fluoroquinolones. In the first generation fluoroquinolones, we have norfloxacin, ciprofloxacin, ofloxacin and pefloxacin. And in the second generation fluoroquinolones, we have 6 drugs, that is levofloxacin, lomifloxacin, sparfloxacin, moxifloxacin, gemifloxacin as well as plurifloxacin. Second generation fluoroquinolones have an extended antimicrobial activity towards cocci and anaerobes, that is the gram-positive bacteria, as well as the second generation fluoroquinolones show longer T-half. If you see the mechanism of action of fluoroquinolones, it is a bit complicated, so kindly concentrate students. This is the double helical structure of bacterial DNA. So once the bacterial transcription has to start, this double helical structure has to uncoil or unwind. For this, DNA helicase enzyme takes the initiation and it starts unwinding or uncoiling this bacterial double helical structure of bacterial DNA. And the point where the uncoiling moves towards is called the replication fork. So when the replication fork is moving forward, the lower part of the double helical structure of DNA gets into a supercoiled form. So here in this picture you can understand what is the positive supercoiled form of DNA. This is the normal structure of DNA in the bacteria. As the replication fork moves forward, these double helical structure gets winded so closely, and this is called as supercoiled form of DNA. So this supercoiled form of DNA creates a mechanical pressure of over the DNA and causes a breakdown of the DNA. So in order to avoid this and favor the replication process of this bacterial DNA gyrase enzyme helps the bacteria to overcome the positive supercoiling and get changed into a negative supercoiling form. So the DNA gyrase enzyme of the bacteria has two subunits, A subunit and B subunit. So the A subunit of DNA gyrase enzyme causes a break in the back segment of the double helical strand. Then the B subunit of DNA gyrase enzyme helps in negative supercoiling, that is to loosen that double helical strand of the DNA. Then again the A subunit of DNA reseals this DNA again on the front side. Here you can see the breakage and here you can see the resealing of the double helical strand after causing negative supercoiling. So this is how the bacteria uncoils itself to form new daughter DNA strands. So here comes our fluoroquinolones to show its mechanism of action by binding to the site of DNA gyrase enzyme and inhibiting the action of negative supercoiling. Thus, the positive supercoiling effect of the bacterial DNA doesn't go away, which produces a strong mechanical force on the DNA and causes the breakdown of the bacterial DNA. So when the bacterial DNA is broken down, ultimately the bacterial cell also breaks down. Fluoroquinolones also exhibit another mechanism of action, especially the second generation fluoroquinolones exhibit this type of action. After the formation of two daughter DNA strands, there is an interlinkage between the two daughter DNA strands. So in order to remove this interlinkage and in order to make the two DNA strands into separate two daughter DNAs, this topoisomerase 4 enzyme comes into play and helps in breaking down the interlinkage between these two daughter DNAs. So here our fluoroquinolones come back and inhibit the action of this topoisomerase 4 enzyme and not allowing the interlinkage of these daughter DNAs to break down. If these interlinkages are not broken down, there will be again a mechanical force created on the two daughter DNA strands, and this mechanical force causes the breakdown of this DNA and ultimately leads to the death of the bacterial cell. So this shows that the fluoroquinolones are bactericidal in nature. Coming to the resistance of this fluoroquinolones, the bacterial resistance development towards the fluoroquinolones is almost negligible. Plasmid mediated resistance is not seen. As you know, the plasmid is a circular DNA molecule which is away from the chromosomal of the bacteria. So this type of resistance is almost negligible, whereas if the bacteria develop a resistance, they may develop resistance by causing mutations in the topoisomerase 4 and DNA gyrase enzyme, reducing the affinity for fluoroquinolones mechanism of action. So students, this is all about the fluoroquinolones classification, mechanism of action and resistance. The content in this video has been exclusively taken from the Tripathi textbook. Thank you for watching my video. Do support women empowerment and please do not forget to subscribe my channel.